Good afternoon. Welcome to course Thermodynamics of Materials. Today we'll take up lecture 135 and 136, and we are discussing last year the delta G0, the standard free energy change for the reaction half N2 gas goes to nitrogen in 1 weight% in liquid iron. So this was Bapu. Hello, hello, hello. বাপু এখন টপেতে তো নীল জেমস ক্লিপ করে করা আছে এবং টপে ইয়েটা কতগুলো কাগজ সাদা কাগজ just see it there on the top on the left thank you exactly this one okay আর ঠিক আছে these others are not disturbed তো it's okay thank you so we are here delta G0 for this reaction, or which you may call it a change of standard state. What is the value for this? And we actually found this last year. We found this. See how to get this? For one temperature T1, this is just change this delta G0 T1 is minus RT1 ln KT1 KT1 is known from this expression where both are experimentally known weight% nitrogen from the nitrogen analysis of iron nitrogen liquid, and pN2 here the pressure that we have actually fixed the pressure. Okay, so pressure is also measurable. So these two are experimentally found, hence KT1 is known. Hence once known, we get delta G0 T1. We are required to find delta G0 in terms of A+BT. So delta G0 T1 is minus R T1 ln KT1. So 1. Okay. Now repeat this equilibrium experiment, means this experiment given in figure 1. Given in figure 1 for a number of this see for a number of repeat for a number of temperatures like T2, T3, T4, T5, etc. We can then, if we have this, if this data, multiple data, number of data, then we can graphically plot delta, find delta G0 is A+BT. This we discussed, and how, if you ask me how you will find this, I'll show you here. Next question, before I take next question, while I'll show you this one, 5 important conceptual topics we are discussing. So I probably can remove this. These 5 topics. The first one I have considered. 4 will be coming. So just here I'll show you something. How will you get this delta G0 once you have this number of, you plot delta G0 versus temperature, and you have to get this in terms of this. These are the data points. So if you actually connect or draw actually a least square line, straight line, Oh, sorry, very bad. Let me draw first. Suppose these are the data points. So this actually you get this gives you delta G0 is A plus straight line A plus BT. This is graphically here graphically. You see A plus BT. This is nothing but delta H0 minus T delta S. So A will be delta H0, A is delta H0 and B is minus delta H0. So anyway, our job is done. That is delta G0 expressed in terms of A plus BT. You will see this data when you will solve this problem, still making problems particularly. There you will see this is given in the form of A plus BT. So you know how the meaning of this. But still another question remains about this first one, this A. What remains? Next question. I started last day, but I couldn't actually. I ran out of time. So next question is how to find gamma N or gamma N0 in iron nitrogen liquid alloy. Remember, I wrote somewhere. Yes, yeah. Hence this is 0. Gamma N is gamma N0. I said, and as a result of which ENN is 0. Okay, this I discussed last day. Gamma N, because it exhibits Henry's law behavior. So this I discussed. Okay, so this part I will, and I said that this will be shown in figure 2. So this is figure 1. This I have not named anything. So I remove this. Next question, take up from here. Take up from here. What is this? Follow this. This is an interesting discussion. How will you get gamma activity coefficient for which this Raoultian activity coefficient? So you have to plot. I am showing you this. Consider it is better. And next question, how to find this? For this purpose, let us write few lines actually. For this purpose, okay. Let me write. Start. For this purpose, we require to plot. We require to plot plot An versus Xn. N versus Xn. N being the A, I have used A, means activity, Raoultian activity. N being the Raoultian activity. Okay. N being the Raoultian activity of nitrogen. Which is here N. In liquid iron nitrogen alloy. Very interesting question and situation. With respect to full, I am giving what is An? Raoultian activity of nitrogen N, rather. Raoultian activity of N in liquid iron nitrogen alloy. So activity means that is a standard state with respect to 1 atmosphere with respect to 1 atmosphere nitrogen gas as the standard state. This is interesting. Last day I said that it is difficult to get the Raoulsian activity. This I said. Get the Raoulsian because it should be the same physical state like nitrogen of Raoulsian activity of nitrogen in iron nitrogen liquid alloy. Then you need liquid nitrogen, pure liquid as the Raoulsian standard state. But that is not possible. That's why we are talking of alternative standard state. But now to have this actually develop this thing, this involves this change actually delta G0 involves actual gamma 0. This is written somewhere, the change of standard state, RTL and gamma B0 etc. So gamma B0 will be involved, and gamma B0 is Raoulsian activity coefficient. So you must have a plot Raoulsian activity, but then how will you plot? How will you have Raoulsian activity here? The problem is digressed. The problem is rather circumvented, bypassed. Yes, Raoulsian activity, but not how with respect to a standard state, Raoulsian type standard state, not necessarily liquid nitrogen. What is that? Very interesting. 1 atmosphere nitrogen gas as the standard state. We are hooking up the activity of N here in the liquid with the 1 atmosphere nitrogen gas as the standard state, so that we can get N. What is the purpose? To find, this is a job now, how to find gamma N and gamma N0 or gamma N0. I will show actually both. So you see gamma, it should be derived from activity A, Raoulsian activity versus mole fraction plot. Easy. But how to get? This is, we are hooking up this activity of nitrogen liquid to 1 atmosphere nitrogen gas as the standard state. That is practical. This is a very practical. 1 atmosphere nitrogen gas, and realistic and convenient and easy and simple and common. But liquid nitrogen, no. That could be also Raoulsian. So Raoulsian has many options. Even Raoulsian standard state has many possibilities. So what are these? Solid, pure liquid. Both are actually not acceptable in case of nitrogen. 1 atmosphere nitrogen. How will you hook up sir? A liquid here and there? Let us see how we do this. Okay, this is important as the standard state. So with a spare standard. Before making the plot, this is the next job. Before making the plot, we'll plot this. Before making the plot, we actually want to people making the let us first establish, before making the plot, let us first establish a n, this an tricky stuff, an a Raoulsian is, what is this? pN2, partial pressure of nitrogen powered half. This, the answer is, this will be the answer, but we'll establish this in the next few lines. then we will be relieved that AN is the Raoulsian activity, and full meaning of AN I have given here. Full AN being the Raoulsian activity of nitrogen in liquid iron nitrogen alloy with respect to 1 atmosphere nitrogen gas as the standard state. So how to do this? For this purpose, I will use this space. This space. This is over. This part is over. Main job is over. But actually, in the discussion, we came across here last day. If you remember, gamma n is gamma n 0. Hence, ENN is 0 and such things. Okay. So this I will explain how to get gamma n and gamma n 0. All these things. Okay. Gamma actually gamma n. Last day, remember, gamma n is gamma n 0. So gamma n is gamma n 0. So the ratio gamma n divided by gamma n 0 was 1. Remember? So Hn is Hn activity, Hn is weight percent n for that purpose. Okay, this is the final line. So this actually the preparatory lines. So initial lines actually was given already. So there is gamma was featuring, gamma was showing there. So discuss this, how to about this. Okay, but this is how first of all. Then we will plot. We will plot An versus Xn. An versus Xn is here. Nitrogen in the iron nitrogen liquid alloy. So this will do. Okay, very good, very good. So as let us establish. No. Let us first establish that An is as follows. As follows. As follows. Give a star here, and here take the star up there. Okay. So what I am. This is the consider the equilibrium. This equilibrium, in fact, once more. Consider the equilibrium. What equilibrium? Consider the equilibrium half. This one I am repeating. Half N2 gas goes to nitrogen 1 weight percent in liquid iron. Okay, this consider this equilibrium. Okay, see this equilibrium. In fact, this equilibrium. Nitrogen gas present in the gas phase and nitrogen present in the liquid phase, and there is equilibrium. Okay, this is equilibrium state. I already said. So this equilibrium. Now what I am doing actually now, if we consider the same standard state, the same standard state which is 1 atmosphere nitrogen gas Raoulsian standard state. We are consider the same standard state on either side. Consider the same standard state on either side of the equilibrium. On either side of the equilibrium. Okay. On either side of the equilibrium. What is this? Okay, fine. Very good. What is the equilibrium? This is the equilibrium. Okay. Same standard state on either side of the equilibrium. Then what we have? If we consider what we get, delta G0 is what? We are giving same standard state. Same standard state. So what is that? What is that? That is 1 atmosphere nitrogen gas. Standard state. For both, I can refer to any standard state I wish. Choice of standard state is purely arbitrary. Convenience. It is a matter. It is a matter of choice. Okay. So I am considering for nitrogen gas, which standard state? The 1 atmosphere nitrogen as standard state. For nitrogen liquid, nitrogen 1% the liquid phase. What is the standard state? We know very well it cannot be nitrogen liquid, pure nitrogen liquid. But for this part, for this plot, N versus Xn plot, and to find N, we are choosing the same practical Gaussian standard state, that is 1 atmosphere nitrogen gas as the standard state. For both of them, if same standard state, now what is the delta G0? Delta G0 is the difference between the two standard states. Okay, so it will be obviously, and then this leads to equilibrium constant is 1 through delta G0 is minus RT ln K, or I think this part, all this, at least this I can remove this, unnecessary already, or 1 is right nicely K equilibrium constant is what you write with respect to Raoultian activity. Remember AN is fully described. Full. When you are asked what is AN, you have to give the full here. AN being the Raoultian activity of nitrogen means N, not N2, N in liquid ion nitrogen alloy with respect to 1 atmosphere nitrogen as the standard state. This is the activity. Raoultian activity with respect to 1 atmosphere as the 1 atmosphere nitrogen as the standard state. 1 atmosphere nitrogen as the standard state. This is the full or short definition of AN. Okay, but you can add this. What is the nitrogen is exists where in the liquid iron nitrogen liquid, or nitrogen in the liquid state, but its activity is referred to a gas standard state, 1 atmosphere gas standard state. No problem, choice, and we have made this. So what is AN? So this will be nothing but here. Follow this equilibrium. AN, consider this equilibrium. Okay, this AN over what is this? This is also AN2 power of, this is the gas. This is gas. Okay, this is the AN. Okay, shall I write this AN? This AN, the nitrogen in the liquid phase. This nitrogen in the liquid phase. Follow equilibrium between this and this, nothing else at the temperature T, namely T1. So this gas, what is this? This nitrogen in the liquid phase. So N, what is this? You know very well. That is the easiest thing to answer. So what is this? Partial pressure. Activity of any gas species is nothing but partial pressure, because its standard state activity is ratio of two partial pressures. One is the state under study divided by the standard state pressure, which is 1. So 100 times you have done this, so no point. This is scale, or AN is pN2 power half, and we are very we wanted to establish, we have established. Next step would be what? I am removing this line too. Next is the plot. Why once we know AN, so how will you get the AN in the system? Get the pN2 pressure, pN2 this at the equilibrium state, and take a square root. In passing, I tell you one thing: nitrogen is dissolved in the liquid iron not as molecular nitrogen but atomic nitrogen. That's why N we use, not N2. Okay, this has been proved that it is in the atomic state. It is in the solution with iron. Anyway, we have established this job. Next is what? Next, what is the purpose? Why we are doing so much? So why are trying to find N? Why you have taken this job? This problem N, finding N. Why? To plot, so that we may plot N versus Xn like activity composition plot, Gaussian. So that will do. And what will we, from which we will get the gamma N or gamma N. Then it will be all clear to us. So slowly, I will show you everything. So now, since N is known in the system, in this equilibrated system, in this equilibrated system, N is known means activity of nitrogen in this state, and also Xn. So the plot will be, you know very well and very well. Recall the beginning lessons. An is AB versus XB. Xn 0 to 1 as it 0 to 1. Just mathematically place this N and draw this line. You know which line it is. This is Raoult's law line. Raoult's law line. What is the equation? An is Xn. Then comes the deviation and Henry's law question. So Xn is what? You just clarify this. An is what? How's partial pressure of nitrogen at equilibrium measurable? Is measurable. So it is already shown. Xn where? Xn in liquid iron nitrogen alloy. Xn is where? In liquid iron nitrogen alloy. In liquid iron nitrogen alloy. Okay. How will you get this? Oh, experimentally measure this. Analyze. Analysis of a liquid sample. Given this, then actually I tell you what. This I should. This is not good. Wait a bit. Hang on. We are very close. This is the deviation from Raoult's law. What is this? Deviation from Raoult's law. What it represents? What is the equation for this? N is gamma N times Xn. Gamma. Yeah. And what is this? In the dilute regime, there is a linearity. Linear. This is a straight line. What is the equation for this? This equation for this, extrapolation, this is a straight line, extrapolation, this is what? This is actually the gamma n0, gamma b0, okay? What is the equation of this line? Like this Henry's law line. Henry's law line. What is that? Tell me. N is gamma n0 x. So from the initial, if there is actually this this is factual line, actual line. N is gamma n x actual line, but initial part is linear, and which coincides with the Henry's law line, or this linearity is given by Henry's law. If it were not linear, then you would say this line, this curve, deviation has never coincided with Henry's law line, has never followed Henry's law line. There is this will consider. This we will consider later on the second case where carbon actually. So here, but here actually we see that this is the dilute regime. As before this, let me remove this in liquid iron nitrogen alloy. This is important. Excellent. This is what? This what you will call this? This is the in the dilute. This is a dilute. This is a dilute regime. This is a dilute regime. Small concentration of nitrogen. So dilute regime. In the dilute regime, what is this in the dilute regime? Okay. In dilute regime, gamma n is how much? Gamma n is gamma n. Remember what I said, gamma n at zero concentration. Since this is a linear behavior, so gamma n is gamma n0 will be valid for the concentration domain, low concentration domain, okay, which will abide by Henry's law. Okay, Henry's law itself is a deviation from Raoult's law. Remember, Raoult's law, deviation. This deviation in the small concentration, in the dilute concentration, it may show linearity. It may show linearity, means that is actually it will actually follow Henry's law. The linearity is given by Henry's law. What is the equation? N is gamma into x. So this segment here to here linear. Then it is breaks into non-linear. Then it is what? Gamma n. What is gamma n anywhere? Gamma n is what? Get the value of an, get the value of xn, take the ratio, get the gamma n for any composition. And gamma n0 is the slope of this, okay? N, okay? Or gamma n you can consider the straight line, no problem. Equation you can handle gamma n0. So both gamma and gamma n0. Now incidentally what? So this everything. This is what figure? We said figure 2. Now everything is here. Okay. This I have not drawn because this is okay. This is actually xn1 is impossible. So that's why I have actually abruptly I have stopped here. This curve. I have stopped here. This is Raoult's law. Okay. Just to show the ideal situation. Okay. This is Henry's law extension. This is the gamma n0. So everything is given. Okay. So both. So two things you wanted to know, gamma and gamma. And what I said, I am repeating for you. The gamma in this case, gamma n is gamma n0. If gamma n is gamma n0, remember here I have removed this Hn. The last lecture I said Hn is recall Fn Hn weight percent. Recall. How many things we commented? Now you should check back. HN Fn times weight percent nitrogen. And what is that? This is the last day. Recall last class. Last class. I repeat it. What is the Fn is what? Gamma n over gamma n0. Oh, by the way, Hn is right. Correct. Gamma n0 times weight percent n. Now this is what gamma. If gamma n is gamma n0 and the concentration domain is actually in the dilute regime, for which gamma n is gamma n0 is valid in the dilute. So in the dilute concentration regime, gamma n is gamma n0. So this is actually cancel out. Okay, this cancel out as weight percentage. And what is the other comment we made last day? This is nothing. Everything is over. Last day, if gamma n is gamma n0, what comment? What inference? What inference? Tell me. What inference? Tell me what inference? We drew last class. We drew in the last class when gamma n is gamma n0. That you see here. So clearly see here gamma n. One thing I tell you, this whole curve is generic name. An is gamma n xn. The whole An is gamma n xn. In the dilute regime, gamma n becomes gamma n0. For this limited range, special condition, status, gamma n is gamma n0. And this concentration is also dilute because we know this. So this is concentration of nitrogen falls here in the dilute regime, and gamma n is gamma n0. That means this last day's class. What inference we drew in the last class? What? Recall. I said ENN is 0. Very interesting. Suddenly jump into interaction coefficients. And hence ENN. And you will see in the data books, yes, ENN is 0. The reason is this. The reason is this diagram. This behavior of nitrogen in liquid iron. This behavior, this experimental condition. This is the behavior, activity versus composition. So what is this? How? Recall. ln gamma n0 Maglorin series plus, go back, this is last class, ENN xn plus, actually we don't write this because for low concentration, omit, drop that, higher powers. Maglorin series actually you can go to any extent, but other xn is small itself, so xn square will be even smaller, so neglect this. If this is this, if these two are same, these two are equal, these two equal, what is the implication? Xn is non-zero, Xn cannot be 0, finite concentration of nitrogen. So what is the comment? Hence epsilon n what is the name of this? What is the name? Self-interaction coefficient of nitrogen in liquid iron. Interaction coefficient. If it is 0, what is this? If it is 0, see here, EBB, if it is 0, if it is 0, then it is 0. So ENN is also 0, and just check this. So this 5 cases, 1 over, 1 over. Similarly, I will take up the second one. Second one. Or shall I'll remove all these things. Okay, no problem, no problem. I will keep this relation, standard relationship for a while, and maybe later. Second, first is over 5 important conceptual cases in solution B. What is the start today? Today, this is today's topic. Okay, this is actually the hangovers of the last class. Okay, of the concluding part of the last class. Are clarifying them. Okay, gamma n 0, etc. Everything. Okay, so B is to find the. Let me write first. To find a similar, but instead of nitrogen and carbon, graphite. To find the delta G0 in the form A plus BT as before, in the form of A plus BT, in the form A plus BT for the reaction or the change of standard state, or for the change of standard state What is that state? Change of standard state. What is that? Carbon solid graphite. Which form? Solid in the graphite form, not diamond. So solid graphite goes to, again, similar underscore 1 weight percent or weight percent, one weight percent in liquid iron. Call it again today. Since we start with this case B. So this is the equation 1. Again, I tell you, this is what change of standard state you call it is Raoultian standard state. So, solid graphite, pure solid graphite, pure graphite, solid. And this is what standard state? 1 weight percent standard state means a Henryan. Henryan standard state, and in addition you can write the weight percent type. The last time also we did this. So we'll kind of remove all this. Okay, remove these figures. Remove these writings. Okay. Start fresh today. Start fresh. Okay. What is the job? Remember, your job is to find delta G0. But additional associated discussion we will also make. We will find delta G0 in the form of A plus B. Start. Okay. So to achieve this, this often you will see in the data book. This equation. So this reaction or this change of standard state data. So you will see how we can measure it, find it out. To achieve this, let us find out let us find out the delta G0 for carbon solid graphite solid. Carbon solid means okay, but it is graphite, not diamond. Is what? Carbon is 1 weight percent in liquid iron. I am giving 1 mole fraction in liquid iron. This is again. This is again. If you want to do this, this is what? This is Henry standard state. What type? Mole fraction type. This is weight percent type. This is weight percent type. This is mole fraction type. Okay. Once we find out this, then we will actually do some manipulation to find finally this one. One. Call this two. Call this two. Call this two. Okay. To study, concentrate on two, and then a little bit of juggling will give us one. Very easy. Very easy. Only difference is what? This to this. I am sorry. This to this. The standard. Henryan standard state mole fraction to Henryan standard state weight percent. There is a standard relation. You should remember this. What it is? Change of standard state. RT-ln activity. I am sorry. RT-ln atomic weight of A over atomic weight of A plus 99 atomic weight of B. A and B is the binary system. Here it is iron and carbon. A is iron, B is carbon. Just I am giving you. So this is not big deal. This you can do. Consider this as if this is the problem. So how to find this? To study reaction to let us perform the equilibration shown in figure. Equilibration experiment shown in figure 1. Shown again similar problem. The problem that we faced in nitrogen. Nitrogen and liquid iron. If we consider that we consider the Gaussian standards, no big deal. We consider liquid nitrogen as the standard state, and that is absurd. That was that we found absurd. Liquid nitrogen absurd. Here also similarly, carbon in liquid iron. So you also say, okay, sir, same physical state for carbon, and then liquid carbon, pure liquid carbon. Will you? This I explained last class. Liquid carbon, impossible. If you heat to melt carbon, carbon graphite, it will dissociate fast. It will sublimate vapor. It will not melt. So impossible. And what is the solution? Solution is the alternative standard state. Convert this. Again, the same question. Even so, you will actually hook up the activity of this. Liquid carbon, no. Liquid carbon, Gaussian standard state ruled out. Struck off. Out. Not, but another form of Gaussian. Last time what we did? In nitrogen case, partial pressure, activity of nitrogen, AN is pN2 power, square root, pN2 powered half, means square root of pN2. We circumvented the problem. We resorted to different kind of Gaussian standard state. No, we knew full well that liquid nitrogen not possible. But nitrogen gas is possible or nanoscale with respect to that. In this case, I tell you briefly, in this case also we will hook up liquid carbon not possible, but another thing we will consider. With respect to carbon, we will discuss this. With respect to what Townsend activity will get this. Okay, let us follow this. Okay, follow the experiment. Okay, this follow this experiment. Okay, this one, figure 1. This is the experiment. We'll hook up with carbon. I'm giving the answer first. We'll hook up with non-liquid carbon, impossible, ruled out. But carbon, act with respect to carbon, graphite carbon. This it is in the liquid hooking up with a graphite carbon. Actually, let me show you, then you will understand more. But at least you understand liquid nitrogen, like nitrogen in liquid iron, hooking up with the nitrogen gas as the reference state. Activity of nitrogen in the liquid state relative to gas, 1 atmosphere nitrogen gas as the standard state. Don't worry. So this I have already told. Start the experiment. You have not so big. This is your crucible. This is your, and you are sending CO2 gas mixture. CO2 gas mixture gas. And what is this? Good. This is the furnace. This is the furnace running some temperature T1 perhaps. T1. What is this stuff? This is what? 50 minutes perhaps. No? This is what? This is what? Initially pure liquid iron. Yes. Pure liquid iron. Achha, wait, it is right. Pure. This is pure liquid iron initially. But as I pass CO2 to gas, it has a carbon activity. This I showed you how to find the activity of carbon from a gas mixture CO2 to carbon potential. Recall carbon potential, Illingham diagram that time, carbon potential, oxygen potential. So there is a carbon potential means activity of carbon. So then activity of carbon, this is pure. When it is flowing over it, means flowing across it and leaving leaving exit gas. What it will do? This has certain activity, finite activity of carbon with respect to graphite as the standard state. That is always standard state matter. But graphite activity of carbon short. There is certain activity of carbon, and this is zero, none, pure iron. So there is an activity gradient. So carbon will be transferred from high activity to low activity. Continuously passing. So carbon will be transferred until the two activities are same. This is called equilibration. Equilibration of this with respect to this. So when both of them, when this will attain the same activity as this gas mixture, then what will happen? If you send, no change, the same activity. Delta G is 0, no change. Chemical potential same, activity same. So there is no more. We say it has been equilibrated already, or thus it has been equilibrated, and there is no point carrying on this. So this we are trying to do. So pure liquid iron we took initially. Then what has happened? Then this becomes initially then it becomes liquid iron carbon. So carbon enters into the liquid iron, becomes iron carbon alloy, because iron carbon alloy, carbon, liquid iron carbon alloy or solution, liquid iron carbon alloy at equilibrium. Try to follow this experiment. So you are equilibrating pure liquid iron with gas mixture, CO2 gas mixture having a which has a certain carbon activity. Now how to get the activity of carbon? I'll outline today also, but you have already read. You have already read. So equilibrium. So what is this? Figure 1, equilibration experiment. Figure 1, equilibration experiment. Happy? Okay. So when it is equilibrated, this becomes iron carbon alloy. And okay. So okay, let us perform this equilibrium experiment. Now I'm writing K is KT2 KT2 KT, okay. I will get delta G0 for this, then finally for 1. KT2 is what? Tell me, write this, okay, is what? Since this is 1 mole fraction standard state, Henryan, so what is the symbol? At equilibrium, Hc, okay, Hc, okay, Hc, and you can write in addition Mf to distinguish it from weight percent Henryan. And what is this is numerator, denominator is what? Activity of carbon. Graphite means solid. You know very well, everyone knows what is this active carbon graphite, and you may add here at equilibrium. At equilibrium, okay. Graphite equilibrium, okay. So what is this? Hc is what? Tell me is what it is? Fc, H, Henryan. Hc is what? Mole fraction. Xc, if it follows the Henry's law, okay, but initially you will not consider this, okay. You have to follow the curve. So you write Fc, and Fc for Fc you don't have to write mole fraction, because mole fraction or weight percent does not matter, times Fx. And what is this? I am writing H. Follow. What's our equilibrium between what and what? This. This gives activity of carbon. This one. See, this. Equilibrium between this and this. This is shown here, and this is shown there. I have considered a Henryan activity, okay, because I already told I cannot consider outside activity of liquid carbon, but so this part, okay. Even so, okay, Fc, and Fc is what? Now go systematically. Fc is what? Tell me. Gamma c by Xc is what? Follow Xc, just right, in liquid iron carbon alloy. In liquid iron carbon alloy, and Ac is like graphite. What is the value? No, pure graphite is solid. Ac solid 1. Students have tendency to give right 1 here. Where is your graphite? Solid graphite where? This has a certain activity of carbon, but does not mean it is 1. Normally it won't be 1. Special case is 1. It can be less than 1. That you have to find. So subject to finding, subject to verification, whether it is 1, less than 1, what? That I said carbon potential of a gas mixture. This not known yet. Okay. So this is there. Now what is? Now keep on doing this. What is Fc? Tell me. Gamma c by gamma c0 no problem, XC, XC and AC. Again you may write equilibrium, if you wish, you can write. Okay. Now what I will say, note all are right hand side is known. All variables are known. All this terms, each term is known. XC is known from the analysis at equilibrium. Analysis, take the sample, XC known. AC, I'll just wait a bit. AC, I'll give you. AC from this, now this is already started. What is the activity of carbon here? That is called carbon potential of this gas, that is here. You have to, that's coming. So this is also experiment. From this gas, carbon potential, this analysis, this gamma C by gamma 0, this is a challenge. Then what you have to plot? Again like this, gamma n 0 today at the very beginning, you have to plot AC versus XC plot. A, Raoult's activity carbon versus XC, not big deal. Okay, then in similar manner we will proceed. Let us move on. Okay, note, note. Okay, what is this? Okay, note all numerator and denominator terms are experimentally known. I'll explain how. Before this, if it is known, then this is known. This is known means delta G0 known, and one temperature, then another temperature T2, then still another, and still another, and yet another. The number of temperatures. Plot, you will get delta G0 in the form of A+BT for the two, and there is a little bit of manipulation. I have already said you will get delta G0, and job is done. But again, there is a gamma C0 is little bit of, actually there is some trouble over there. You have to clarify concept. So that I will take up. Okay. But I have said experimentally known. You will see also experimentally known. Already I have shown gamma n 0. So similarly gamma C 0. But slowly. Okay, it is almost done. Quickly. So let us to illustrate. AC graphite. AC graphite. Gr is graphite. Is solid, carbon solid. AC solid is known from the delta G0 data of the reaction CO2 gas plus carbon solid. Carbon solid means carbon graphite actually. Solid means graphite. Solid is graphite. Graphite and solid interchangeable. Graphite, Gr is graphite. Short for graphite. And this is also solid. So interchangeably. Solid is 2CO gas for this reaction. 2CO gas at the temperature T1, at the temperature T1, at the temperature of interest, and with known compositions of CO2. Give me, you say 60 40, 60 CO 40 CO2. Temperature T1 is 1000 Kelvin. No problem. Actually, you can find. How will you remember? This is your carbon potential. Finding the carbon potential of a CO2 gas mixture, or for that matter, oxygen potential. Is that discussed? Here, for a delta G0 gives KT1, PCO2 from the composition and the total pressure. Then AC is the unknown. So this is found. So this is obtained from this. Okay. So this is done. Next is what? The values of then the problem actually. This is in bracket here. It's okay, I think. Okay. This the values of what remains now? This gamma C and gamma C0. The values of gamma C and gamma C0 are unknown where AC versus XC plot, activity composition plot. Okay, very good. Unknown from the unknown, okay, known as explained in figure 2. This is okay. So gamma C0, I will explain figure 2, and what else? AC here, I have explained AC here, and XC is what? As I already told you, I am writing also that experimentally measure from the analysis of the sample, of the liquid sample, iron carbon sample. XC is obtained known from the XC analysis of liquid iron carbon alloy. After equilibrium has attained, okay, because I have tagged equilibrium, KTO equilibrium. So figure 2 then remains. How to get gamma C and gamma C0. Okay. Acha. Now finish this. Supposing you have no trouble with gamma C and gamma C0, which will be explained in figure 2, then if all terms on the right hand side are known, then the left hand side is known. Hence KT2 is known. Proceed. Hence KT2, sorry, KT2, oh, hence KT2 is known, which yields what? Like last time, which yields like like last time, like last delta G0 T1, which is equals to nothing but R T1 ln K T1. Okay. Oh, I'm very sorry. One suddenly KT2. KT2 is okay. KT2, which gives delta G0 T1. T1 okay. KT2. I'm talking up to is delta G0 T1. T1 means this is the temperature. Is minus RT ln K. KT1 is known. Oh, that's right. This is wrong. It's okay. It's okay. Oh, KT2 actually don't confuse. Don't confuse. If KT2 is known, you will get corresponding delta G0. KT2 is known, delta G0. What should I write? Actually, I should write here KT. Here, follow this. It is T instead of T. What temperature it is specified? T1. KT1T. So this is actually then KT. Hence KT1. T1 is the temperature. T is the general name, but T1 because I'll change to T2 and T3 and T4. KT1 2 means for this KT1 2 is known, which is what delta G0 T1 2 for the 2 is what minus R T1 ln KT1 2. So delta G0 T1 2 you know. Now then what you will do? One data you have got, then you produce another data and still another, yet another, so on. So repeating. So then it is next is repeat. So repeating the experiment delta G0 T1 2, correct? Repeat this. It's better we repeat this, okay? To find the delta G0, I cannot change this. I am removing this part, this part. The values of gamma C and gamma C0 in figure 2, that is coming. So only here I am writing, take this. I don't want to disturb. You draw a line here, just here. Repeating this experiment, given in figure 1, given in figure 1, given in figure 1 for a number of temperatures T2, T3, T4, so on, we can graphically find delta G02. 2 in the form of A plus BT. Shall I? I'll show you. How will you again? This case, how will plot this? Delta G0 versus T plot. Delta G0 like last time versus T. Data, 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 data. Delta G0 is A plus BT. That is delta E0 minus T delta S0. This all discussed, you know this. So, but the problem is not yet over. I mean, first segment is even the first segment is not complete because this is for 2. Our target is 1. So we have to make little bit of manipulation. So that is next. Okay. So this part is also what you will do. Here I am writing. Here I am writing. Okay. So this actually. Acha. But I like right where? Yeah. Continue. Finally, so see our aim is 1. Delta G0 1 in the form of A plus B. Finally, we can find delta G0 1 in the form of A plus BT in the form by adding with Acha, I am just removing this. Just I am writing here gamma C and gamma C0 to find gamma C and gamma 0 figure 2. If I this I will take up. So I am removing this. I am removing this. Okay. By adding with delta G0 2, how will you arrive delta G0 1 from delta G0 2? Just add here what you will add? This one on the left hand side. Carbon 1 mole fraction in liquid iron goes to carbon 1 weight percent in liquid iron. This is 1 mole fraction to 1 weight percent. If you add this, then mole fraction cancel. You will have carbon solid graphite. Here also goes to carbon weight percent. So that I am writing. With delta G to what you have to add by adding the delta G, the delta G0 for the change of standard state, for the change of standard state, what is the change of standard state? Carbon, write this to where? This to this. Carbon 1, just copy this, Carbon 1 mole fraction, 1 mole fraction in liquid iron goes to carbon to this, carbon 1 weight% in liquid iron. Achha, here you may mention that these are all both are Henry and standard state. These are also Henry and standard state. So from one Henry and standard state to another, mole fraction to 8%, what is the standard? Recall, as I told you, is RT-ln activity of, I am very sorry, every time I make this, RT-ln atomic weight of A over atomic weight of A plus 99 atomic weight of B, the standard. This change, standard, okay? Henrian standard state 1 to the other Henrian is what? Is nothing but which is RT-ln atomic weight of A means here iron solvent, atomic weight of iron plus 99 atomic weight of the solute, which is carbon. That's it. That's it. That's it. Now I will actually take up this one, gamma C and gamma C. This is okay. Okay. Next, I give a double star. This is very important. Yeah. The last issue. So this is over. So we have actually found delta teacher in the form of A+BT. This problem is over. Okay. So I remove this so that you understand that everything is over. Only this is all over. Okay. All over. This. Okay, remove this. Let us see. Remove this. Remove this. Let us see. Only the top heading is there. So this is okay. This is over. Okay. Next, last gamma C and gamma C is I said. So this is the plot of double star. The plot of AC versus XC. AC and standard state is graphite versus XC is shown in figure 2. Oh, I'm sorry that I have removed the figure. I was afraid there will be some is shown in figure 2, which gives the values of gamma C and gamma C0. Note in passing, here gamma C is not gamma C0. Even in the dilute state, gamma C unlike gamma N is gamma N0. Recall, and the consequence is ENN is 0, and gamma N is gamma N0 in the previous case. What is the reason? The reason I have written previous case. That is the meaning of this. That is the iron carbon liquid solution does not exhibit Henrian behavior even in the dilute regime. Happy? The biology. Acha. It just I'm now giving that figure. Activity of C, the famous figure AC, XC. But you have to be careful. What is the AC? AC is what? AC is what? Acha, right. 0 to 1. 0 to 1. This is Raoult's law. Raoult's law. AC is XC. Then we have a deviation. This is the best I could do. This is the deviation from Raoult's law. What is the equation for this? AC is time. AC is gamma C XC, as you know. What is this? This point is gamma C0. I'll give the equation. What is the equation? AC is gamma C0 XC. Henry's law. This is Henry's law. AC is XC, XC. Okay. So what happens? How do you get this? See, even in the dilute regime, there is no merging. There is no actually overlapping of this curve and the Henry's law. The actual curve does not fall on the Henry's law. Even in the very small, no. From the very beginning, from 0, it has moved away from the Henry's law. Previously, nitrogen, for the dilute regime, it fell on the Henry's line. It falls on the Henry's line. But here, not. Acha. By the way, if you ask me what is this point is, this is your gamma C0, not bad to write this. Gamma C0, this point. This you know very well. This you know. Okay. It's okay. This I have not drawn. Actually, there is no meaning of this. This XC is where? By the way, write this. How you get this XC? AC, how do you get this? We can write easily AC. Who finds us AC? How do we get AC? AC is what? With respect to graphite as standard state, means Raoultian standard state. That's why A Raoultian. Please follow. I have removed the figure. Okay, just I am showing you quickly. This was the figure. Iron carbon liquid, and what is flowing? Incoming CO2. So follow XC. How do you get these points? These are the actual data points. How do you get AC from where? From the gas mixture. You are applying this AC, and what is the outcome? XC here, which was initially 0, pure iron, where it has taken at equilibrium, certain XC at equilibrium, this value. We change actually, AC keeps changing, if you keep change actually, then it will change. But for each value of AC, there is a corresponding equilibrium value. Okay. So and these several ACs are plotted, and you get this activity composition diagram from which you get deviation from Raoult's law, and from which you get gamma. Gamma C. This is generic name. AC is gamma C XC. As I told you, you can find gamma C anywhere. It's nothing but AC divided by XC. AC divided by XC is the gamma C. And AC 0 is this. How you get this? Since there is no actually overlapping, a coincidence of this line and this line and this line. How to get this in this case? What is in this law line? Take a, this is the slope of the tangent. Draw a tangent at XC0. Draw a tangent to the curve, to the actual Henry's, to the deviation from Raoult's law, to this curve. This is not Henry's law. Henry's law line is this one. How to get this? Draw a tangent. There is no linear part. Though no linear part, it doesn't fall on Henry's law. So draw a tangent at X. This I explained. X is 0, and that will be your Henry's law line given by SC is gamma C0 XC, and this point is gamma C0 corresponding to X is 1. So this okay. So gamma C and gamma C0 are found to find gamma C and gamma C0. So I repeat, AC is clearly written, X is not clearly written. X is where, as I told you, AC here, follow. AC here and XC here. Analysis. So what you write this? Write this very nicely. XC in liquid, iron, carbon, alloy. This is XC, liquid, iron, carbon, alloy. Okay. Very good. Very good. This is figure 2. As I mentioned, figure 2 is okay. So now actually you have the finishing lines. Okay. So noting that this is additional line, noting that gamma C is not gamma C0. Noting that not only that gamma C, which is greater? Which is greater? Gamma, this is a gamma C, this is a gamma C0 line. AC is gamma C XC, AC is gamma C0 XC. So for giving XC, gamma C is actually above the gamma C0 line. So that means gamma C is not equal, I have already said. So if gamma C is greater than gamma C0, what inference you will make? We will make some inference. We can infer eCC, and hence eCC, and hence eCC is non-zero, and not more than that is positive. eCC is positive, and in fact, if you get this data, eCC data, okay, you will find this is positive, non-zero positive. How you get this? From this relation, ln gamma C is ln gamma C0 Maclaurin series, again plus eCC XC, again ignoring the higher terms of XC for dilute solution. Maclaurin series ignoring higher terms higher powers of XC, higher terms now, higher powers of XC. After all, this is a dilute solution. See, actually, saturation is actually dilute solution, maybe What is this actually? 2% in austenite or say 0.8. You see, carbon is actually in the range of 0.8 to 0.2 to 0.8, all these things, okay, or maybe 2% for this saturation, or 4.3% maximum, okay. So dilute, okay. Even so, it doesn't fall on Henry's law line. Anyway, this is ignoring the higher powers of Xc, or suppose you are considering that is saturation, highest value. When activity of carbon is less, it will be even less, and it can show small, it will very dilute, and even dilute, very dilute, it doesn't fall. So that means it is not equal, means greater than from the figure, and hence eCC Xc, higher powers of Xc for dilute solution, okay. Hence this. For dilute solution, ignoring the higher powers, for dilute solution, what comment you have? You have see, this is greater than this, So it is greater than this is greater than this. That means what is the comment? For any value of eCC is a positive quantity. If it is a positive quantity, then gamma C can be greater than X. Gamma C0 for any Xc value. Xc is a 0.1, 0.2, 0.3. So gamma eCC must be positive. Give you the value. I give you the value. eCC is positive. Remember, positive. Small maybe, positive. What is the eCC? Experimental data in book. Data in book. In data book. ECC will be more commonly used than epsilon cc, but is what? 0.12. The note here, this is a positive, and you are satisfied. You are satisfied with all explanations. Data book ECC is 0.12. Okay, let me check once more. Sorry, I was doubting this. Is 0.22. We'll use this in this next assignment. Still making problems. ECC is 0.22 positive, and also you have shown that this ECC is positive because this is additional talk. Our main aim was delta G0 in the form of A+BT. That has been already completed, and but we clarified our concept, particularly all these things. This figure is very useful for concept, for the purpose of concept, and okay, and how to this also. The first segment is also how to find delta G0, and in this context, alternative standard state. Thank you. This part is over. Okay, let us take up the next issue, which will be relatively simpler. So remove this over, I guess. So remove this D4, and keep this pretty, okay, only results. I'll give you important result. Okay, so that actually, anyway, good. So this is now C, A, B, C. Okay, C is what? B, C. To show that, start. Since I'm going to start that just little bit later, give me the caption. See, to show that now all we actually okay, move your mind from this discussion. Okay, your new topic coming, new subtopic or topic, new issue. total altogether new, to show that Wagner's interaction formalism interaction parameter formalism, in short, E formalism in short, E formalism, epsilon formalism, and later on I will give you E formalism. Okay, for the epsilon formalism, in short, is thermodynamically inconsistent. To show that, remove all this, remove this. So actually, this is I often actually, or previously, I a number of times I told you that Wagner E formalism, but you see how it is, how it is. Start with this. It's better actually to go for. Let us consider a binary solution AB. A is solvent, B is solute. A is solvent, B is solute. For simplicity, we will later extend to the multiple component. But for the at the beginning, you consider binary. For simplicity, for which you already have, for which already have the following quadratic activity coefficient versus composition relationship. What is that? When you have quadratic, you recall ln gamma b is what? Ln gamma b 0 plus epsilon bb xp minus half xb square. I hope I am correct. Yes, I am correct. Okay, correct. Okay, it is equation 1. Call it equation 1. Okay, and for the solvent, ln gamma a is what? Tell me. minus half epsilon BB equation 2. These are known. Okay. So up to quadratic. So we have not gone beyond quadratic. See, you see, this is this for a dilute. One thing note at the beginning that Wagner E formalism is about a dilute solution. Dilute concentration of solutes. Example, very good example to metallurgist, to the metallurgist, steel. Steel is a dilute solution. Iron the major, so 98%, 99%, and the others are small, so 2 to 3%, okay, or like this, okay, in steel actually. So we apply there. Wagner has given a relationship which is valid for dilute solution, but we will show that there is some trouble, that is that thermodynamically inconsistent. If we have approximate somewhere, then it will actually violate somewhere else. Some approximation, but how serious that violation is, that we will consider. I will comment on that. Remember, final two things, that Wagner interaction parameter for dilute solution one, and we will actually profusely use Wagner's formalism. Because often we apply these to steel compositions and which is actually dilute with respect to solutes. So little bit approximation may be there because actually, but with small error maybe. But this is the summary. Let us see. For a dilute solution, gradually build up this. For dilute solution, for dilute concentrations of solutes, as a note somewhere, that I mentioned that it is for 10 minutes, because that's good enough. For dilute concentration of solute B here, the quadratic concentration terms, there are not many here quadratic, only one quadratic. The quadratic concentrations term, okay, here one, and the for solute say this is quadratic, this is not. So quadratic concentration term in equation 1 is negligible, resulting in the following simplified linear form, which is Wagner's E formalism. So underscore for dilute concentration of solute. So Wagner formalism is about dilute concentration, dilute solution. And why is that negligible? Quadratic term. If again I told you, if xb is small, if xb is small, say point 1 say, so xb square even smaller, 0.01. If xb is 0.1, which is small, xb square is 0.01, which is more negligible. So less. So we'll neglect that higher powers. This is the reason. This Wagner did and simplified the relation, and which was very useful. And we will solve 9 problems in assignment 11, still making problems, and all each case, in most problems we will consider Wagner's formalism. Okay, see you later. Okay, so what is this? Then what it becomes? Ln gamma b is what? Tell me. Ln gamma b 0 plus EBB xp, because xp square gone. But remember that is approximation. But this approximation will not invite much error, will not introduce much error, negligible. But problem is what? Theoretically difficult, thermodynamically inconsistent. This is one. So approximation gives this. This term drops out or neglected out. Okay, good. Ln gamma b is this, and ln gamma a is what? 0. Okay, for same reason, and which yields accordingly we get we get uh, which gives me these two gives what? Give what? Which two? These two give the above two, above two relations give the last two relation give what? Xa d ln gamma a plus xb d ln gamma b. How much? Try. Remember, recall. This is, remember, gives dm. So what it is coming here? Xa d ln gamma b. Ln gamma a is 0, means first term is 0, plus xb d ln gamma b. This is a constant. EBB dxb. This is what? Is non-zero. Is non-zero. Why? Since EBB is typically is non-zero. Nitrogen is special case. Okay, is 0. But self interaction is actually carbon, for example. Okay, so many all actually have positive or negative. So non-zero, and xb cannot be finite concentration. Xb is non-zero. So what is the meaning of this? This is non-zero dxb. Okay, so non-zero. So it is total thing is non-zero. But Gibbs dual equation says what? Xa dln gamma a plus xb dln gamma b is 0. But it is non-zero. Violates Gibbs dual, which is also called thermodynamically. What is this called? equation of thermodynamic consistence. Okay, I am coming to this. So that is this gives you is violated. Why this violation? You understand now? This does not violate. 1, 2 does not violate gives to m. In fact, that was see this never violates. This approximation makes it violate. This is that conceptual trouble, not very practical trouble, theoretical trouble. Okay, so let me write is 0. Hence the Gibbs-Duhem equation, which is also known as thermodynamic consistency equation. Thermodynamic consistency equation for a binary system. I told you for binary there is no difference between Gibbs-Duhem and thermodynamically thermodynamic consistency equation. But in term there is a difference. Gibbs-Duhem is one and thermodynamic consistency equation that we found today or last class different. But this which is for binary system does not hold good. That means Gibbs-Duhem is violated, so people will object. Does not hold good under this approximation. Under this approximation. Underline this. So under this approximation it does not comply with the Gibbs-Duhem. Remember this to original. No, it actually complies with the Gibbs-Duhem. But when you actually approximate for dilute solution, dropping off the higher terms, square, quadratic terms, later on you will see XB, XC, if a ternary system, XB, XC is also quadratic. So drop them. If you drop them, this simplified. This is very simple equation and very attractive for us. Particularly when multi-component system we will consider, I will give that. Then it is very attractive and useful. And as I have already told you, we will use them profusely in our skill making problems, solution. And when you have actually dropped this, these are actually not following Gibbs-Duhem equation. And Gibbs-Duhem equation and equation of thermodynamic consistency is the same for binary system. So it is called thermodynamically inconsistent. So, but comment is that even so we will use. Even so, that is also important. Even so, the last line. Even so, Wagner's formalism for its simplicity is very popular and frequently used in solving dilute solution such as steel, such as steel, such as steel, numerical problems, dilute solution, numerical problems without incurring much error, without